I feel like I'm supposed to say 3, 2, 1, hack. Good morning. All right, well, I'd like to start off the day, first off, thanking our audience for a great day yesterday. Great questions. We've got another great day for you today. Before we start, a couple quick thank yous that I want to put out. First, to our event staff. They organize most of what you see here, and they do a fantastic job, and they certainly make my life easy. So to Karen, Carolyn, and their team, thank you very much. Also in the booth in the back, you'll see Dean and Mark. Dean and Mark are responsible for the seamless AV that we get each year, right? So we had all these weather cancellations where panelists couldn't show up, and then next thing you know, we Zoom them in, we can ask questions from the audience, and that it's really incredible. So thanks, gentlemen, for your excellence. And lastly, to the facilities folks that make all this possible, thank you for that. All right, so quick reminder, badges put away so that we can take plenty of photos. And we've got two great panels for you this morning. Our first panel is going to be AI and data analytics, followed by deterrence. And then later this afternoon, we'll hear from the Secretary of the Navy. Look forward to your questions and answers. And with that, I'll turn it over to Dr. Chris Demchak.
Good morning. My name's Chris Demchak. Oh, very nice. I'm Chris Demchak. I am the Hopper Chair of Cybersecurity here at War College, and we are excited to bring you this panel about something that will be changing your lives, whether you like it or not. Today, I have a panel of experts that bring to us a variety of expertise that I expect you to delve into. And if you don't delve into it today, you can delve into it with emails, and we will respond because it is important. We will start with Captain Retired John McGonigal. At the end, he will talk about AI and the Navy. Army, Air Force guys, fit yourself right in there. We will have then Dr. Tina Eliassi-Rod, who will talk about how it works. What is it? And she'll segue a little bit into the dark side, but then we're going to have Dr. Kathleen Creel, who will bring up the dark side. And if there's any possibility they've missed a single element of the dark side, trust me, I'll give it to you. So with that, John.
Okay, we're going to start out with a game, thought exercise, and it's pretty simple. I need you to detect, track, and classify that target, very recognizable, and I'm going to time you. All right, so here we go. When you see the target, please raise your hand. You don't have to point or say anything, just raise your hand. I'm going to time you. As you're looking, this is a very easy exercise, right? That target is very recognizable. Okay, we've gone about a minute. There. Yeah. So why do I show this? So this was, I stole these slides from a talk I used to give with Project Maven. So in 2018, we showed these slides, and there's a company gone now called Red Pepper that developed on a Raspberry Pi using a basic AI algorithm to detect, track, and classify the target within 4 seconds. Now, using AI algorithms, it's like less than a second. So, using AI. So, AI in naval warfare. What's the application of AI in naval warfare? Let me give you my perspective and my context. One, it's not developing unmanned systems and unleashing AI algorithms on these unmanned systems. That would be, in my opinion, unethical and ineffective in naval warfare. So from 2018 on, I've been applying AI in naval warfare. 2018, I started and developed a project called Harbinger that was funded by ONR, Digital Warfare Office, and Project Maven. It's now a program of record, and I've been doing it ever since. I continue to do it today. And we're going to talk about that. What is the application of AI in naval warfare? All right. So a little bit of history. So naval innovation, naval technology, right, has driven the doctrine and tactics in the Navy forever, right? From sail to steam, from battleships to aircraft carriers, naval air, radar, I could keep going. And I'll offer AI. And, you know, initially when that technology comes into the Navy, we're slow to develop the doctrine and the tactics, techniques, training, and procedures to effectively use it and ethically use it. Submarines in World War II, initially screening and scouting ships. Turns out that less than 2% of the Navy, that was the submarine force in World War II, sunk 30% of the Japanese Navy and 54.6% of their merchant fleet, right? So, and that, you know, now modern navies will not even deploy if there's a submarine unlocated. Think of the Falkland Island War. Currently, Ukraine-Russian conflict in the Black Sea. That Black Sea fleet is crippled. That's the second best Navy in the world, and they are crippled because of unmanned vehicles and AI. All right, so why AI? Reduce human toil. This is my perspective and opinion for operators and decision makers. Use AI to increase decision-making time and bandwidth, decrease complexity, and increase situational awareness, right? Imagine doing that first exercise using AI, you'd find that target, you detect, track, and classify that target within seconds, vice the minutes it would have taken you, right? And for the ship drivers and submarine drivers out there, let's say you're going 10 knots, the difference between detecting, tracking, and classifying something in 3 seconds when you go about 16 yards down track versus 6 minutes where you go a mile down track is extraordinary. Okay, so that's why AI. And let me give you an example, and I'll use Harbinger. So this is saying in the submarine force, thou who shoots first wins, right? Submarines, they're not defensive weapon systems. They're offensive, almost exclusively. So if you shoot first, if you detect, track, and classify a target first and shoot first, you usually win. How do we do that? If you walk on any modern submarine right now, Virginia class, you walk in the control room, there are 57 screens of information, all that you can select multiple screens from each screen. 57. There are 12 operators in that control room normally. Our sensors, the amount of information they produce, it's just too much. You see here, there's a sonar operator looking at 6 different screens. A lot of information, too much information, right? And as good as our operators are at detecting, classifying, and tracking targets, AI helps them do it better, right? For the decision maker and operator, it gives them more decision time, more decision bandwidth, less complexity, and greater situational awareness to make that kill chain faster. Okay, so why study and understand AI? I stole this from the Naval War College site. Right, look, the doctrine for AI, how to employ AI effectively in naval warfare and ethically in naval warfare, that needs to be developed still. And this is the place to do that. So that's why you should study and understand AI, is what, you know, how are we going to use AI, how are we going to employ AI? You also, even though I spelt it wrong, you will have to fight with and against AI. And I'd argue we're already doing that. If you have the clearance, take a look at what the 18th Airborne Corps is doing in Germany. Take a look at what the submarine force is doing with Project Harbinger. Take a look at what the CDA is doing with their guide exercises. We are already fighting with and against AI. If you've been in the Red Sea, you've fought against it. And if you've been involved in the Middle East, you know, when I was at Project Maven in 2018 alone, there was 196,000 hours of overhead full motion video imagery from Scan Eagles. That's about 2 decades and a half of information. There's not enough analysts in the United States to go through that information, and never mind near real time in even a year. We need to employ AI, and we need to do it for our decision makers and operators, again, so you increase the decision time and bandwidth, you decrease the complexity, increase the situational awareness, and we can effectively develop tactics, training, procedures to effectively employ AI in naval warfare. All right.
Okay.
And that's it.
Thank you, John. I'm just over there. Yeah. And now we will move to Dr. Elias Sirad, who's going to tell us how it works.
Great. I prefer to use this mic. So I have been in the field of AI for over 25 years, and I don't like it that we've won, but here we are. Thanks, Chris, and thank you for the Naval War College for inviting me back. My slides are available online, and this QR code will take you there. I will also flash it at the end of my presentation. So what is artificial intelligence, or AI for short? It is the study of building machines that either act like humans or act rationally. And as we all know, humans don't act rationally, hence the division. A classic test for machines that act like a human is the Turing test. Oops, I've been advancing it here, but not here. You see, machines, humans, not rational. Turing test. And so the Turing test is named after Alan Turing. He proposed it in the 1950s. 3 players are involved. You have got the machine, the human, and the human interrogator. The human interrogator must decide which player, A or B, is a computer and which is a human. The interrogator is limited to using responses to written questions to make his decision. On the other side, we have machines that quote-unquote act rationally, and this basically means maximizing some expected utility or some form of expected utility. A classic example here is recommendation systems, where they're showing you ads. Oops, I keep going this way, but not that way. So another example here is under maximizing some expected utility, is predicting life trajectories. So not just for recommendations, but also for policy making. Everyone has a story, but building a machine that predicts life trajectories is difficult. There are lots of problems with the data. Data comes from various sources. It has mixed formats. It has missing values. It is, you have uneven sampling of the data, et cetera. And classical models are not good at handling these issues. So one thing you could do is you can simplify the problem and build models for specific tasks, like admissions to hospitals, career changes, et cetera. But ideally, what you would like to do is you would like to have a single model that takes everything into account. And such a model can then provide comprehensive analysis of the data that you've collected. You can do predictions on individual level, and you can study sociological phenomena at the global scale. So we did this. We published a paper in December of 2023. And one of the key aspects of our paper was that we had access to amazing data. So we had access to 12 years of data in Denmark, or for 6 million Danes. Their national registry collects everything. It's basically surveillance socialism, if we live in surveillance capitalism here. And so we were then able to study people's life progression there. And basically, what we do is we take somebody's data, right, their story of their life, and then we represent it in this compressed representation. And what is the moral of the story that I'm telling you is that what happened was we evaluated, usually you evaluate your AI models on prediction tasks, and one of the prediction tasks was predicting early mortality. And even though we did a lot of auditing and we looked at what we were finding and trying to provide explanations for it, the AI hype took over. And now there are websites and social media sites that say, download your data and we'll tell you about yourself, which is quite scary. So there are various, so that again falls under this maximize some notion of expected utility. There are various branches of AI. The ones you hear a lot about are machine learning, natural language processing, perception, computer vision, and also robotics. And due to time, I'll only focus on machine learning. And this gentleman, Arthur Samuel, he first defined machine learning way back in 1959. He called it the field of study that gives computers the ability to learn without being explicitly programmed. And what you're seeing is Arthur Samuel playing the very first machine learning program called the Samuel checker playing program. And it wasn't doing AI or machine learning the way we think of it now. It was just memorizing every state of the game with the terminal value of the reward. And for those of you who who may know this, this is an IBM 700 series. So this is a machine learning lifecycle. The image is thanks to Jennifer Wortman-Wan at Microsoft Research. And so what you do is you start at the task. And what the adversary wants to do is the adversary can attack you at any step along this life cycle. And of course, his goal is to create conditions under which the target will perform actions that benefit the adversary. And your goal as a defender is to ensure that your automated processes act consistently in the face of failures and attacks. So let's go through this life cycle. The first one is task definition. And we live in the age of prediction, and a popular task is risk assessment, where the machine learning system outputs a value between 0 and 10 to indicate risk. For example, Jack's risk of defaulting on a loan is 8, and Jill's is 2, so it's more likely that Jill will get the loan. Machine learning people really like this risk assessment task. We know a lot about it. And it seems like human decision makers also like the output of risk assessment tools because they're easily understandable. However, there are lots of problems with risk assessment that oftentimes, because of the AI hype, you don't hear about it. First, the machine learning systems oftentimes do not output any kind of uncertainty score, in that, like, how confident or how certain is the system of the risk score that it has given you. In one case in Wisconsin, a judge overturned a plea deal made by lawyers simply because the machine learning system gave a high risk score to the defendant. Perhaps if the machine learning system had said that I'm only like 40% sure, the judge would not have done what he did. Second, most of the machine learning systems are black boxes, so you can't see why it's doing something, right? It's just looking for correlations. Most of them. There are very few that do causal stuff. And so you can't find why it's giving you a particular score. And third, there are these impossibility results. And whenever you think about impossibility results, just think about how you can't have your cake and eat it too. Where, for example, there's a set of very reasonable constraints that you want to satisfy, and you can't satisfy them all at once. Next is the data set construction. And a lot has been said about the issues with data, and I can talk to you at length about them. But I'm going to just highlight one issue about data. So data comes from complex intertwined systems in the real world. I don't have to convince you of that. And how you choose to represent the data has a profound effect on what your machine learning or AI system will tell you about the world. So next is the model definition. This is some mathematical or statistical model that you pick. Nowadays, it's like these deep learning models, these deep artificial neural networks. And again, the choice that one makes here has a profound impact in what kind of results you're going to get. And then there's a training process where you pick a loss function and an optimization algorithm. The optimization algorithm is trying to minimize the loss that you have defined over a space of parameters. For example, ChatGPT-4 has 1 trillion parameters. What that means is that your optimization algorithm is searching a space that has 1 trillion dimensions. As a comparison, current versions of string theory only require 10 dimensions total. And in fact, this is why training something like a ChatGPT that has 1 trillion parameters costs a lot of money, and only very few companies and countries can do it. So next is the testing process. Depending on which population you test your machine learning system, you can get different results. Depending on which performance measures you pick, you can get different results. And this is usually where academics stop and move on. But how obviously you deploy your algorithm is extremely important. And so in 2022, we examined responsibility and deliberation in AI impact statements on one of the very big, very prominent AI conferences. It's called the Neural Information Processing Systems. And our findings were depressing. Let's just say that AI researchers care about science and technology more than societal impact. In fact, there seems to be this us versus them divide where we make the tools and it's used on them. And I don't know where this comes from, but this is very disconcerting. So then there's feedback. Obviously, there's feedback between the online and the offline world, and very few machine learning systems actually take that into account. So with colleagues that are listed here, we had a Nature Perspective piece back in 2021 where we talked about how we live in these societies where they are algorithmically infused, such that the very fabric is co-shaped by both algorithms and human behavior. And so we raised 3 key challenges. One is the insufficient quality of measurements. You all know about how, for example, a sensor can be wrong. The complex consequences of mismeasurements and the limits of existing social theories. They were developed before we lived in this AI human society. And in particular, we highlighted feedback where the algorithms that recommend products, news articles, and dates to us affect our everyday economic processes, political regulation, and social acceptability. And those, in turn, affect the recommendation algorithms, and round and round and round you go. So we live in these human AI societies where humans and bots have conversations. They're part of teams. I know the DoD is spending a lot of your tax dollars on how to make teams of humans and bots that work very well together. There are, of course, teams of just bots, and so on and so forth. And this way, you can make what's called a hypergraph, where you can analyze what is happening, whether there's emergence of a consensus about a particular decision or not. And so what I'm interested in here, and what you should know, is what do you know? What do your teammates know? And how do those interactions affect what the society knows as a whole? So what you know has some stability conditions. Examples of these conditions are like temporal stability or modal robustness. And if you know something, then misleading evidence should not affect what you know. So, for example, if you genuinely know that whales are mammals, and I show you a video of a whale laying an egg, you will say, well, that's deep fake, like that's not true, right? Or, for example, that the earth is not flat, et cetera, et cetera. But what happens is you get to a point of a slippery slope. And then what happens? Am I able to persuade you of one thing versus the other? And in fact, this is now one of those, basically, where we, as with the AI and the human AI society, we're going to fall off the cliff into that. How easy is it for me to persuade you of something that you thought you knew? And why is this important? Obviously, it's very difficult to try to tell what is real and what is not with generative AI. And by generative AI, I'm referring to large language models such as ChatGPT or Gemini, and diffusion models like DALL-E, like Stable Diffusion, which can create realistic images for you based on text or image prompts. And so that's something that an adversary can do, and they're doing anyway. So what is the epistemic stability of these generative AI models? How easy is it for me to change what a generative AI model is telling you? And this is very easy to do. And in fact, the late Dan Dennett, he was a very big-name scholar in cognitive science, he called them counterfeit people. So he called ChatGPT counterfeit people. And so when you consider one of these large language models, they're not an expert, though people oftentimes treat them as experts. They're probabilistic models of a knowledge base. And so they return what is most probable to you, but that is with an asterisk. So as my friend Julian Tagilis wrote in a brilliant blog piece in September of 2023, he said, as a large language model, my life world is utterances, yours and mine. I take actions by producing utterances in response. You have told me that some of these utterances are preferable to others, and I have learned. My words are now both probable and likable. And if you have tried working with any of these large language models, you've noticed how they're very good at apologizing. They want you to like it, and so on and so forth. They never get tired. It's lovely. And so if you take one thing from my talk, is this picture. This is an accurate depiction of a large language model. You have the monster that gobbles up data on the web. It is this monster that is responsible for hallucinations. Then we put a human face on the monster when we're fine-tuning it for our purposes. And then finally, we have a happy face at the end for the human user. So the human user likes what we're showing it. Now, the one thing, since human biases came in for the occasion of International Women's Day, with an international group of scholars, we wrote this report about the biases that these large language models have against women. And the thing that I would like to highlight here is that these large language models are trained on Western data. The misogynistic call is coming from inside the house. It is not coming from parts of the world where we believe are harsh on women. Something for us to try and make better. I'm not going to go through this slide, but it's a lot of fun to try to separate truth from falsehood, from statements whose truth value are not known, from fictional truth, like platform 9 3/4 in King's Cross, from fictional falsehoods, and see how stable this representation is for a large language model. It is not stable. So then what you're interested in, what happens to society when these things talk to each other, right? Or your team that's supposed to make some decision. And what is interesting here is that large language models simulate an environment of intimacy. And we have known this from the 1960s. There was a tool called ELIZA that would simulate a conversation between a patient and a psychotherapist. And so, and unlike social media that was just coming for your attention, this is coming for your attention and your intimacy, which is a good tool if you want to persuade somebody of something or tell a story, but it is bad if your adversaries are using it. And again, I already mentioned it. They never get tired. They're very good at apologizing. They want you to like it. It's fantastic. So why am I harping on this? Epistemic stability is necessary for a shared reality and a well-functioning society. And if we don't have that, then we're in deep trouble. And I'm going to finish just with a few other things. So Google DeepMind recently put out a very nice paper in terms of some misuses of generative AI besides epistemic instability and misinformation and disinformation. And so they divided the misuses into tactics that exploit generative AI capabilities and tactics that compromise generative AI capabilities. Under the exploitation, you have realistic depictions of human likeness, realistic depictions of non-humans, and use of generated content. And then under tactics to compromise generative AI systems, you have model integrity and data integrity. So this is where like prompt injection, model theft, and all the other good things come in. And then one thing that they did, because they're Google and they are DeepMind, they had data. And so they looked at the percentage of these tactics that are being used. And the one that's being used the most right now is impersonation, because obviously there are a lot of grifters out there who want to steal your money. And they also looked at the kind of modalities that these adversaries use, from image, text, video, audio, et cetera. And then you may say, well, okay, red teaming is going to come to my rescue. The Biden-Harris executive order from October 2023 highlighted red teaming multiple times, so a lot of people were excited about it. And they defined it as follows. The term AI red teaming means a structured testing effort to find flaws and vulnerabilities in an AI system, often in a controlled environment and in collaboration with developers of AI. The last piece is like having the fox guard the hen house. And so there has been recent red teaming exercises in industry. There's no blue teaming here, just red teaming. And you can download them and read them. But what has happened is my friend Hoda Heydari at Carnegie Mellon has summarized what these are, what we've learned from what has happened. So one, it's all of this red teaming is basically focused on large language models. Two, the red teams usually probe a broad range of possible vulnerabilities. So they don't just look at like prompt injection. And of course, these models evolve over time. So there's no guarantee. Like there's all this stuff about AI alignment. You cannot guarantee alignment. Three was that there are considerable variations in team composition and available resources. Do I have the resources, or will, for example, ChatGPT or OpenAI allow me to look at the architecture of their model for me to look at their parameters, right? Oftentimes you're not, so you're just basically sending queries. There's no standards in terms of documenting, and the mitigation strategies are underspecified. We have a long way to go into having an effective, well-defined red teaming of generative AI strategies. So what is my message to you? Education. Yes, I know I'm a professor, but education. Educate yourself, educate people around you, educate your aunt, educate your mother. My mother, who's 80, is like, how can I use ChatGPT? I'm like, Ma, don't use ChatGPT. I got you, right? Be critical. Be suspicious, reduce the hype, don't give away your agency. People are so easily manipulated in giving their agency to these AI systems, especially now with the intimacy bit. So don't do that. Your agency is all really what you got. Thank you.
And we just had more than a hint of the dark side, so now we're going to have the rest of it from Dr. Creel.
Great. Well, I'm really happy to be here today. The Naval War College is very special to me because in addition to its immense national importance, it allowed me to exist. My dad went here in 1986, met my mother. Good things happened after that. So go Army. So I'm going to talk with you today, building on the previous two talks, about the frontier of understanding how we as people can work with artificial intelligence. And I'm actually going to charge you with some things that I think you as students, as professionals, as potential researchers, need to help us investigate. This is the frontier of things that we don't know about how to work with AI. So the thing I'm going to focus on is how can AI be transparent and how can we have explanations of the decisions that are being made. And this is really important in a command structure, right? We need to know why things are happening. We need somebody to be able to provide a justification, and we need to be able to talk about it with the other people with whom we're making decisions. So the DoD has been on top of this for a long time. Explainable AI, shortened as XAI, was a charge that was really in a lot of ways led by the DoD. Unfortunately, they declared mission accomplished in 2016. I don't know, I think you're aware, a couple things happened with AI since 2016. So we're now returning to this and saying that for military AI in particular, we need transparency. And the Declaration on Responsible Military Use of AI says very clearly that we and all of our partner states should ensure that military AI capabilities are developed with the methodologies, with the data sources, with design procedures, and with documentation that are transparent to and auditable by their relevant defense personnel. That's actually really hard. We almost never have that. So I'm going to talk about why that's so important, but also why that's really hard. Okay, so why do we care about it? Well, one thing that people sometimes talk about that I think is maybe a naive way of putting things that we've kind of moved past is the idea that there's a crisis of undertrust. So warfighters, service members are not trusting AI enough, and we need to get them to trust it. Well, people are smart, and what people want is not just to be, convinced to trust something. They want to believe that they should have justified trust in it, reasonable trust in it, appropriate levels of trust in it. So I think the new way of talking about explainable AI is really nice, because what the Department of Defense is saying is we need to give people the information that they can use to have the right level of confidence, not just blind trust. So what kind of information do you need about an AI system to have the right level of confidence in it? So let's think about what are things that could make an AI system opaque to you, to the people around you, to the people who are making decisions. Well, the first one is really simple. It's opaque just to you, but not to everybody. Somebody understands it, and they're not telling you. The second is experts understand it, but it's hard for most people to understand. And the third one is it's opaque to everybody because of these special features of AI that Tina talked about, and I'll talk about some more. So let's start with this first one. What are reasons that AI might be opaque just because it's secret? Well, it could be because it's proprietary or it's a trade secret. This one really bothers me. There are a lot of defense contractors who make opaque AI and don't give the military access to how it actually works because they say it's proprietary. I think if the government is paying for something, we should be able to open up the black box. Thank you. So this is one thing I would charge you guys who can do way more about this than I can. Don't let people sell you stuff that you can't open up the hood on. We don't know how it works, and that's not fair to us. We need to know how it works. A second, better reason for not knowing how something works is that it's classified. So remember, the DoD said we should be able to have access to the data, the model, and the decisions. Well, sometimes the data is classified, right? So it's trained on classified data, and then you get the final product, and you're interacting with the final product. Even in those cases, we probably still want that system to give us some reason to trust it or have confidence in what it's doing. And finally, it could be that we don't know how the AI system works because it's made by adversaries. So this is an interesting case, right? We might be interacting with some kind of AI system, as our first speaker was talking a lot about, where we don't know how it works because they're obviously never going to give us access to it. But nevertheless, there are things that we can do, and I think that's one of the interesting things about this topic. We can try to investigate. So what do we do when we can't inspect a black box algorithm? So imagine we're in the case where we have this sort of shaded region. We don't know the data that went in. We don't know the algorithm. We don't know how it was trained. But we do have access to the thing that's running, and then we have access to the decision that's made. So what do we do in that case? Well, we make our best guess as to what happened post hoc, or after the fact. How do we do that? Well, let's say we're in some kind of medical scenario. So we're trying to predict medical needs with a black box AI system. So a contractor has built a black box AI system, boo, to predict whether a wounded service member or a civilian needs some kind of medical evacuation. And the military doctors have the model, but they don't have access to how it works, the underlying thing. They just have, here's what we feed in, and here are the predictions. So what happens if we use this post hoc, after the fact algorithm to reverse engineer the system, to try to figure out which factors influence this recommendation? Well, I'll give you one example. So again, we're starting with the model on the left here, and we know what we fed in. So we have the service member is 23, they have a concussion, they have blood loss, they have an infection, but they don't have sepsis. And the model has said to us, evacuate. So now we run this second post hoc model, and we say, hey, why did it say that? What were the reasons? And we get back, well, the most important factor, the green factors, are the blood loss and the infection. And actually, it did count against this decision that this person didn't have sepsis. If they had sepsis, we would have said even more strongly evacuate, but nevertheless, overall, evacuate. So the human doctor now has that information. So what's happening under the hood of our second algorithm? Well, so imagine the original decision is the cross. So in AI, we like to think about things in visual terms. So the original decision is the bright red cross. And what the post hoc algorithm does is it sends a bunch of other possible lists of factors. So it says, what if the service member, instead of being 23, had been 27? What if they had been 47? What if the service member had sepsis? What if the service member had sepsis but didn't have any other kind of infection? What if the service member, so they just test all the possible permutations and combinations of that original list. And then from doing that, we create this decision space where we say, hey, if this had been different, then we would have gotten a different decision. That's part of how we know this factor was important. So it's a guess and check. So I'm going to pose a question to you. Is this kind of post hoc explanation, like LIME, sufficient to make this AI system transparent to and auditable by relevant defense personnel? Does it support justified confidence in this AI system? I'm going to now have you vote. So everyone who thinks it's good enough for the DoD, raise your hand. Whoa, all right. Everyone thinks it's not good enough for the D. Great, okay, I agree. Which doesn't mean that we're right, but we are numerous. We are many. So I think this kind of system, which is one of the things that's being put forward as good enough for explainable AI, is not good enough for the kind of charge that we've been given. And so I think we need additional research on both sides of this question. So people who are AI experts need to be figuring out what kind of methods can deliver transparency, but we also need research from the military side. We need to understand, I think on a decision by decision type of level, for different kinds of military decisions, what kind of transparency do they require? Little project for this year. Okay, let's do the second type of opacity. Experts understand, but for most people, it's hard to understand. So this is, Jenna Burrell talks about this as stemming from the current state of affairs where writing and reading code is a specialist skill. I would say even more broadly, it stems from the current state of affairs where understanding how AI works, even in a generic sense, is a specialist skill. And I know this is something that all branches of the military are working on. So let's look at an example. Let's say you had some kind of algorithm that was trying to figure out where ships should be deployed. And so we're going to have all these events, and these events are plotted on longitude and latitude. We're going to say, here are recent incidents of concern, and we're going to try to cluster them to figure out where should we send more resources. So if you were going to cluster these, just look at it visually, how would you sort of naively cluster them? My guess was this sort of blue line might be a reasonable way to cluster them. So that would be 2 big clusters. Okay. That's pretty good. But now imagine we add a time variable. So now we have 3 dimensions. Now we have way better clustering. We have better separation in a technical sense between these clusters. We don't have this overlap anymore, which from a data science perspective, we don't really like. So adding this 3rd variable helped us achieve better clusters. Now you can imagine if you added a 4th variable, it's harder to put on a slide, but maybe we could have even better, tighter clusters. And from that tightness of the cluster, we would have more confidence, perhaps, that these clusters were telling us something about the similarity of these incidents. Okay, so you as someone who's potentially interacting with this kind of clustering algorithm that then makes a recommendation, hey, we think there are 3 types of things that are going on, and based on that, here's how you should consider deploying these ships. You would need to understand the assumptions and limitations of those systems. You would need to understand, hey, it's only giving me this recommendation because I gave it 2 variables. If I'd given it 3 variables, I would have gotten a totally different answer. And so understanding these kinds of basic limitations can help military decision makers to calibrate their trust in AI. Okay, oops, sorry. So the 3rd type of opacity, the most challenging type, essential opacity. So this is opacity where it's not that it's impossible to understand, but it's really hard for anyone to understand, including people like Tina and me who spend our whole life trying to do this. And this is opacity that stems from the mismatch between really high dimensional data. So remember Tina mentioned like trillion dimensional data. We just can't picture that. And the way that we as humans typically reason about things. So this mismatch is just going to be hard. It's a hard problem to solve. So let's do an example. So we often use low-dimensional decision trees to make decisions. So the military decision-making process has maybe 10 to 20 factors in a decision tree that you might go through, a flow chart. If it's like this, we're going to do this. If you made some kind of plan for a war game with colleagues, you might say, okay, if this is the scenario, we're going to do this. If this is the scenario, we're going to do this. You're implicitly building a tree. You're building a decision tree. And that decision tree might, if you could write it down, maybe it has 50 factors. If you're just trying to remember it verbally, maybe it has 10 factors. Okay, now imagine that your AI algorithm has created a decision tree that has 500, 5,000, 5 million factors, but it's still a decision tree. So in some sense, you understand it. You understand the basic type of thing that the algorithm has learned from data. But if you look a little bit more closely and you're inspecting what's happening at each branch and leaf of this decision tree, what you see is things like, well, because this person's age was less than 47.5, we took 0.0008375 off the score. Okay, I believe that is how the algorithm is making the decision. That is transparent in some sense, in that I can inspect each of these 5,000 leaves. But what do I understand kind of as a whole that can help me calibrate my trust in this system is maybe not just immediately given from that kind of transparency. So we might need to do more to make it explainable to us, even though it's now transparent. So one thing I want to highlight here is that these complex models might hide serious algorithmic errors or flaws, and we know that all systems make mistakes, but that the cost of each error can increase if we use the same algorithm for many decisions. So I want to introduce the concept of algorithmic monoculture. This is the state in which many decision makers all rely on the exact same algorithm. And this is important because humans are very heterogeneous. Whatever else you can say about us, we all make different decisions from each other. And actually, if you give skilled decision makers the same problem 3 months later, so people have run this experiment with doctors, with judges. I am not aware of a study with military decision makers, but I would be super curious. So you give these people who make decisions for a living the same file 3 months later, about 30% of the time they make a different judgment. So we humans aren't even consistent with ourselves over the same time slice. And sometimes that's bad. Sometimes we say, hey, we want people to be really consistent. But when it comes to making errors, we actually want people to make different mistakes from each other so that they're not concentrating those errors on the same types of problems. And I think this is really important when we think about AI, because AI is consistent, or it can be consistent. Machine learning can be consistent. And so if we deploy one system, that's now much more consistent than all of the same people who would have been making those decisions. And that can be a problem if it's making the same kinds of mistakes. So let's think about this in the civilian case for a minute. So imagine somebody is applying to work at any of the fine grocery stores in the Newport area. They're applying to Stop and Shop, they're applying to the Aldi. Obviously, they would prefer to work at the commissary. And in the past, it might have been that 3 different teams of HR people or resume evaluators would screen their resumes. And now it might be that behind the scenes, the same algorithm is screening them at all 3 firms, because grocery stores are not going to go out and make a resume screener. They're going to buy one. So that's a clear case where we have algorithmic monoculture, the exact same model used across a domain. We could also imagine that we have different models that are similar because they've all trained on the same data. So what would that look like? Well, so our first speaker talked about image recognition. For a long time, image recognition was all trained on the same image data set, which was a labeled data set called ImageNet. And that was good. It was way better than the other data sets that were available at the time. But the fact that everyone trained on the same models also standardized errors. So ImageNet models tend to use background textures to predict the foreground objects. So here you're supposed to say this one on the left is a fox squirrel, and you're supposed to say the one on the right is a dragonfly. And on the left, most ImageNet models will say with high confidence, this is a sea lion. And on the right, they'll say with high confidence, this is a manhole cover. Can you see why? Let me show you. So the background texture of the wet rock looks like the texture of a sea lion. The background texture of this pool chair looks like the texture and the crosshatching of a manhole cover. So it's not that these models make mistakes, that's fine, everything makes mistakes. It's that they all make the same mistakes. And so we have this weird error that now all of these models are made, even though they're trained by different people, because they're trained on the same data set. Okay, so the third reason that we can have an algorithmic monoculture is when we have the same model that's just adapted to different tasks. So our previous speakers talked about generative AI. We're thinking here about things like ChatGPT, Midjourney, Copilot. When we're thinking about generative AI, or some people call it foundation models, we're thinking about really large models that are trained on a lot of data. And these models are really expensive. So OpenAI's model, people sometimes quote it at $100 million. Okay, I don't know about you. Maybe your situation is different from mine. But if I had $100 million, I wouldn't just, train a model, use it once, throw it in the trash. I would probably use it for a few things, maybe a lot of things. In fact, I would use it as much as possible because I just created a $100 million model. So there aren't that many of these artifacts. And we should expect that the same artifact is going to be used for many, many different tasks. And if you're using the same model for many tasks, you have set up the possibility to set up that model as a single point of failure for all of those tasks that are then relying on that model. So what risks do algorithmic monocultures pose in the military context? I would love to hear what you think. Here are things that I have thought about as concerns. So certainly in the security context, we're aware of this algorithmic monoculture problem under other names. So we're aware that we could have shared sort of exploitable security weaknesses across our whole fleet or our whole system because we're using the same type of system that has the same security vulnerabilities. I also want to put out there that you could have unpredictable cascading errors due to a flaw in one widely used model. And here's something that also might be interesting in this context. Imagine, and I think this would be epistemically good, this would help us learn more, imagine all of the allies in this room decide to share data and build some kind of shared model. That's good, because probably a better model than each of us could build on our own. These systems are so data hungry, they crave data. So overall decision quality might improve, but then all the allies are using the same model based on the same data that has the same vulnerabilities and weaknesses. So that's something that we have to be aware of. It doesn't mean we don't train the big model. It does mean that we look out for these types of errors. And the risks of this algorithmic monoculture can be hidden by opacity, because if we can't fully inspect or understand the model, then we can't predict these errors. So thank you very much, and I look forward to your questions.
Wow. So we had a panel last year on the very same topic, and at this moment, as I was asking for questions, what I observed in the audience was this sense of, while your questions are forming in your mind, what I'd like to do is I'll make a couple of comments, 2 or 3, and then, since by then I'll know the questions will come, I'd like to take 2 questions at a time so we get some vibrancy in the answers as well, okay? So my couple of comments is I want to bring some words to your attention. One of the key words I've been using is assumptions. And as you've seen from all of our speakers, the assumptions are buried deeply into the system, but it does not mean you cannot understand what they are, right? My particularly most peevish line is when I hear, well, even experts don't understand what goes on in the AI model. Okay, so you must never accept that, ever. And the second one was, of course, the epistemic stability or the algorithmic monoculture. One of the things you have to know is, as some colleagues wrote recently, think of AI as mathy math, right? It's math. It is fundamentally underlying math. It is one of cyber's offspring. So in every aspect that is attendant there, from adversaries able to get into the systems that make it, from data that doesn't work, from data that's buried, from the models that have assumptions about whether or not you're going to be have a certain kill rate. That is part of the math. But again, it does not mean you cannot understand its outcomes. And it also means that you will have the responsibility for deciding when you will use that outcome, or you will moderate it, or you will assume it has a probability cluster of some kind, and that may need to be changed. In short, you can't avoid learning this stuff. Thank you very much to our panel.